So SNNGP, another term for this is unchimeric assistance. Unchimeric assistance. To understand this, let us see the situations first. Suppose I'm trying to compare the rate of solvolysis. Okay. Now, if you compare this one, PHS with a chlorine here, but instead of PHS, I have CH3. Then this molecule reacts 600 times faster than this molecule. Similarly, there is OTS. I have to remove this. Okay, react with this one. Correct. And same thing, we have PHS and CH3. Then this reaction is almost 3000 times faster than this one. Similarly, here also, I have OTS, OAC and OTS here reacting with CH3COH. This reaction, this reactant will make the reaction 670 times faster as compared to this one. Structurally, they look exactly same, except that they are like geometrical isomers. But this has very high reactivity. Now, what's happening in this? Let's understand. Okay. Similarly, if I take this molecule, it would react almost 10 raised to power of 11 times faster than this reaction. Whenever you want to react with, you know, acetic acid here or here, you want to react it with acetic acid. But which means these groups are doing something because of which the rate is so high. So you can see some halides or tosyls are found to undergo substitution at a faster rate if the third or fifth position from the reactive carbon occupied by species like this. Remember, third or fifth position. If third or fifth position is occupied by these kind of species like PHS, OAC, NME twice, only pH, COOH, CO minus, Br, O minus, not OH, O minus, or any pi bond on the third or fifth position. On the third or fifth position, if at all there is any pi bond also, you will notice suddenly there is an increase in the rate of the reaction. Okay. How does this happen? Let us see mechanism. First reaction, let us see this here. This is carbon 1 position where the leaving group chlorine is leaving. This is second position and this is third position. Now, when we add it to water, we are expecting water to uh, replace chlorine at this point via SN2 mechanism. But instead of directly water attacking, internally, the lone pair present on sulfur itself will act like a nucleophile. It will attack, removes chlorine, and you'll get an intermediate of this kind. This is an intermediate with sulfur having positive charge. It has now connected onto position 1. So this is 1, 3, and 2 position. And once this intermediate has formed, then water molecule will attack on one position and the bond will break here. S will regain back its structure and OH has come on this point. Okay. So NGP mechanism happens two times. First, SN2. Every time there is an SN2, we expect there is an inversion. So I can say first we will have an inversion here. We can notice that there is an inversion because first time there is an SN2 reaction happening at this place. Second time again an SN2 happening back at the same position, right? This time with the other nucleophile. Again, one more time if the inversion happens. So inversion plus inversion will always become retention. So it is back to undergoing retention here. So retention can happen in this case. Okay. Let us see one more example. Suppose if chlorine is to be removed here, from the back side, sulfur can attack and this is the intermediate you will get. And now water can attack at this position, water can attack at this position because both of them are equivalent positions. So I'll get one product like this, which is retention, one product like this, which is on the other side of it. But if you Notice structurally they look exactly same, which means I'll get 1:1 ratio for this one, and that would be racemic mixture. So in such case, when the cyclic structure is formed and both sides of the groups are similar, then there is a chance of getting racemic mixture. I hope all of you understood this point. So NGP is a two sequential SN2 reaction. That means first an internal SN2, second is an external SN2. Internal SN2 is what we call it as NGP, neighboring group participation. What are the conditions? For NGP, leaving group must be anti to the other group. Okay, leaving group and the attacking group should be anti to each other. For NGP, concentration of external nucleophile should be less, otherwise normal SN2 can take place. So in case if the nucleophile is stronger, then we can expect another reaction can happen here. It means SN2 can also happen here. Got it? Let us see this case one by one. Here we know that 1, 2, on second position, if you have a lone pair carrying group, then there is no NGP. It has to be on the third position. In this case, it is a simple SN1 mechanism. So we will get product as CH3O with OR here, okay, plus HCl. This is the product, which is a regular SN1. But now if you notice the lone pair is present on the third carbon, third position. And while chlorine is leaving, from the backside, lone pair of the sulfur can attack. So we'll get product as S like this, connected with positive charge. Cl minus have lost, plus Cl minus. And on this molecule again, ROH will attack. It could attack on this position also. It could attack on this position also. Any position is equivalent. So I'll get this as pH. S, as it attacks, this bond will break here. So S methyl group, this group, and then OR group. Okay. This is the product you will have. So basically it has happened two times. First internally substitution happened. Then again externally substitution happened. See the third case. OTS is a leaving group. ACOH is a nucleophile. But now what happens? Internally the pi bond itself will attack here to remove this OTS. Again, you notice that this is position 1, 2, and 3. On the third position, I have a double bond. When you have double bond on the third position, the pi bond will attack. And you would get a situation like this, where we have benzene attacking on both ends like this from this position. It get positive charge here, double bond and double bond like this. Plus TSO minus. And once you get this attached here, now ACOH will attack. ACOH can attack on this position also. It can attack on this position also. When it happens, the bond will break on this side or bond will break on this side. Either ways, depending upon where it is attacking. What is the product I'll get? I'll get this benzene. Now, benzene back. And that could be connected to OAC. And the same structure I'll get one more time. We have like this OAC. But notice this. Here, this carbon was different, right? This was a different carbon. This was a different carbon. So now, this is a different carbon. This is a different carbon like this. So the attack of this is 50-50%. 50% of this one and 50% of this one is a product. Okay. So OEC could have attacked on both ways, both directions, and chances of getting those are 50-50%. So 50% of this and 50% of that you will get. Same logic here. This is position 1, position 2, position 3. On third position, we have sulfur. So the lone pair will attack. Chlorine will leave. So I will get this as CH3, CH2, sulfur connected with CD3, okay, connected with CH2, and these two bonds have been closed like this with a positive charge here. Here it is CD2. Yeah, here it is CD2, CH2, and the bond has been closed here like this with a positive charge. Then H2O can attack on this carbon also. It could attack on this carbon also, so that this bond can be broken, or either this bond can be broken. So I'll get two products here again. So I'll get this as CH3, CH2, S, and if CD2 is there, then we can have CH2, OH here. This is one product. Other product is CH3, CH2S with CH2 is here. Then it would be CD2 and OH. These are the two products that you can observe. Clear, everybody? Questions will be asked about this only, that how much products you will get, what are the types of products you will get, what is the percentage of products you will get. Okay. Those who already have the notes, copy this, make a note of these products. Are you all done? Check out next question. Fifth one. OAC is here. OTS is here. OTS is a good leaving group. And OAC on the opposite side. When you have opposite side, then there is definitely SN NGP can happen. That means you will notice that the lone pair on this oxygen will attack here, remove out this OTS. So the intermediate which I will get is like this, with this group going here with O, AC with positive charge. Then ACOH will attack either on this side or on this side from the opposite direction. So therefore, the product what you will have here is OAC here and another OAC here, or OAC could be inside here and OAC could be outside here. The chances of getting both are 50-50%. So this is the racemic mixture. But when you take this case here, like in the first case, it is SNNGP. But in the second case, now this OAC is not on the opposite side. It is on the same side. OTS and OAC are on the same side. If they are on the same side, then SN-NGP will not happen. Now here simple ACOH will attack here and remove this OTS via SN2 mechanism. So only SN2 mechanism is observed here. So this OAC will remain, and here OAC will come from the opposite side. So 100% only one product you will have. You will not have this kind of racemic mixture anymore. Got it? Same way. Here you see OTS and N-methyl group. They are on opposite direction. Here they are on same direction. This is via NGP, while this is not via NGP. Okay, this is not via NGP. This would happen via SN2 mechanism. So therefore, rate 1 will be greater than that of rate 2. Okay, as SN-NGP is internal attack. Internal attack. Internal attack will always happen faster than the external attack. That's why the rate of the reaction will be high. Thanks. Next. Here you can see on the third position, benzene is present. It can attack from backside. So we would have structure like this. Okay, with methyl here. Okay, and another methyl here. Got it? So now OAC plus here, double bond, double bond. ACOH can attack on both the sides. So I will get product like this. I'll get product of this kind where we have OAC on one side. Okay, sorry, methyl on one side. Methyl on one side. And this methyl on the same side with OAC on the other side, opposite side. Okay, and benzene will be back. Similarly, benzene with OAC on the opposite, this one methyl is on the opposite side. This methyl is on the opposite side as well. And OAC is on the other side, like this. So these are the two products you can extract. Here. Next. Check out here HBr in the presence of CCl4. Okay. HBr in the presence of CCl4. You can look at it here. OH2 will leave here first. Internally, you can see bromine can be attacked. But for that, you need to change the Fischer projection. So HBr is here. Just to show that it is on the opposite direction, I can change this Fischer projection to this side, where bromine can be observed like it is attacking from the back side. So Br will attack from the back side. OH2 is removed. It is like a structure which is formed here. And from there, you will see, sorry, Br minus will now attack and bond will break here, or it can attack from this and bond can break here, either ways. So you'll get this product and which will eventually be turned out into this one. Now, if you notice that originally this OH and Br were erythro to each other. These are erythro to each other, correct? And after HBr reaction, now both the bromines are on the same side, which means they are again erythro to each other. Clear? So if there is NGP, everybody, erythro remains erythro and trio remains trio. Okay, so put that as a note. In case of NGP, in case of NGP, okay, erythro will give erythro product, and trio will give trio product. So that is what you need to understand in case of erythro and trio. I hope this example is clear with NGP. So you can see if you have erythro, right, then I will get mesoform, which is erythro as well. If it is trio, I'll get two products, which is trio as well. Next, if you notice NaOH and Ag2O moist, check it out. NaOH is a strong nucleophile. OH minus is a strong nucleophile. Since it is a strong nucleophile, the attack happens on its own and Br will be removed out, right? So more of SN2 is favorable here. I'm not saying NGP doesn't happen, but SN2 will be majorly happening more than SN-NGP. Okay. Next, if it is about Ag2O moist, okay, in case Ag2O moist is there, so here water will also compete as a nucleophile, and water is a quantity wise, water is more here since it is moist, and water is a weak nucleophile. When there is a weak nucleophile, it is more likely to happen via SN-NGP. So that is why. Now the mechanism will go like this, where we will have double bond O and OH here with Br being present here, isn't it? So the lone pair on this would attack here, removes out bromine. Okay. So that makes the molecule something of this kind, where we have oxygen getting connected like this with OH and plus charge. And then water molecule will attack on this position, breaking this bond. Okay. So which means we will have COOH here, right? Sorry, not there. Here, C double bond OH here. And then this group will be retained. Originally where it was, that is what it will be retained as OH. Got it? Next. In 10th one, if you notice, first when you have NH2, NaNO2 will make it diazonium salt. About diazonium salt, we have learned earlier that when you have RNH2, if you treat this with mixture of NaNO2 and HCl, that will form HONO2, HONO, okay, HNO2 basically. In HNO2, this will be positive side, this will be negative side, okay, and lone pair will attack here, and OH minus will take away H plus from here. So we will get something as N triple bond. First we will get this N double bond, sorry, NH, then we have N double bond O. Afterwards, if you remove the water molecule, you will get this as R N triple bond N plus. This is called diazonium salt or diazonium ion. And diazonium ions are highly unstable. They will easily come out as N2 gas, leaving behind carbocation. Generally, they leave away carbocation. This is what we are expecting. Now, what is the product that you'll take that will happen is this. Check. First, N2 plus when it is present, this one, diazonium salt, before N2 could leave, the lone pair from the other end will attack, making it as an NGP case. And then the OH minus present in the solution or water present in the solution will attack here, break this bond, and converts into this retention product. So the final product, what you will get is an alcohol with a retention product. Any doubt here, everybody? Please check. This is a very important case. 9th and 10th are very important cases. Learn that properly. Okay, you just need to know that you are applying uh, retention on that and due to NGP, and that's how we will get this product. Clear? Right. See the 11th case. I have OTS here and I have OTS here. Okay. First time when I do SH minus, because this is not a donating group which has lone pair or anything like that. So first will be a normal SN2 mechanism. So this bond will break here. So we will get this as CH3 CHOTS with CH2 twice with CH3 with SH. This is what you will get. And now for before the second reaction, the lone pair present on sulfur can attack internally, remove this group. What is the ring size now? Sulfur 1, 2, 3, 4, 5. Okay. So it is a 5-membered ring. So you will notice that sulfur is making some kind of a 5-membered ring here like this. Okay. And there is a methyl group connected on this one. And where the sulfur has attached, there is also a methyl group here. Okay. And sulfur is a part of, sorry, this methyl is here on sulfur. Got it? Hmm. There is a methyl group with carbon. Yeah. So I will just mark out for your information. I'll just mark out this carbon. This carbon is this carbon. And if you notice, here there is hydrogen. Here there is hydrogen on this. And this carbon has a methyl group on it, like this, the way it is being given. Clear? With positive charge here. So this is what you will get first. And once you get that, now the OH minus has the ability to attack either on both sides. It can attack on this carbon or it can attack on this carbon so that it can break off again with sulfur. So what do we get as a product is CH3, CHOH here with CH2 twice, CHSH and CH3. This is the product you will get. 12th one, you can see lone pair on nitrogen can attack here, remove the group. So we will get nitrogen with two ethyl groups on it and also makes a bond like this with a positive charge on it. With one side we have R. Clear? This is the product you would have. And if this product is further continued to react with water or something, then water will attack either on this end or on this end. Usually the major product will always be on the less substituted side. So it is less substituted. So we'll get this as N and ethyl with this R group here. And then we have OH group on it. So this is the R group. So we have major product as this one. Done. Everybody make a note. Recognizing SN NGP is important. Where exactly it is happening is important. Okay. Finished? See the pi bond as neighboring group. In this case, I have OTS group connected this way. This undergoes acetylysis faster than B. Why? See, the pi bond itself can connect here, removing this OTS. So the neighboring group here is the pi bond. Okay. You can notice this. This is position 1, position 2, and position 3. When you have it position 3, when there is a pi bond, and that too, it should be on the opposite direction. OTS is leaving from here and it is the one here. But this side, it is on the same direction. So pi bond cannot attack from the back side here. This is not possible. So therefore, here SN-NGP can be observed. Here SN-NGP is not observed. In A, pi bond and OTS are in anti-position. So you can see how it can happen. OTS is leaving. Pi bond can make a temporary transition state like this, a non-classical carbocation. And afterwards, this is that non-classical resonating structures. Then ACOH will attack on it. The bond will go back. So we will get this as OAC here. So we will get a retention product of 100% of this one. And I told you that in case of cyclic structures, right, the rate of SN-NGP is very high, 10 raised to power of 5 times greater. So A is almost 10 raised to power of 5 times greater than that of B. Clear on it, everybody? Check out next one. Sigma bond as a neighboring group. Sigma bond as a neighboring group is like this, where we have, imagine OBS is moving from here. OBS is moving. So here the sigma bond, like how it can be related here is it will remove out this hydrogen bond. I mean, it will break the bond with hydrogen temporarily and makes a support towards OBS. So as OBS is relieving, the carbon will make a support temporarily, correct? And then a nucleophile will approach here, right? Nucleophile will approach here, getting back to the products. Okay. Now this is not on the anti direction, so here only SN2 is favorable. Okay. So let me show you with an example. Suppose if you have an example given this way, and I have H here and OTS here, correct? And I'm trying to treat this with, ROH, alcohol. Clear? So first thing what you will notice is that this carbon itself will attack here, trying to leave the bond temporarily with hydrogen, because of which you will get an intermediate like this. You will get an intermediate like this, okay, with hydrogen here. Clear? And hydrogen almost here is delta negative charge, and this has, because this has, sorry, delta positive charge here, and the bond is almost closing between these two like this. Okay. Then a nucleophile, in this case ROH will come, ROH will attack on this carbon, breaking this bond back, and this will take away this H plus. So again, what do we get here? It will be like this. Hydrogen bond is back here, and this hydrogen is the same, and OR will attack from the same end. So you can see the retention has happened. Where OTS was, the same end OR has been come. So this is how the NGP works in sigma support. Okay, sigma bond as a neighboring. Clear, everybody? So this is about SN-NGP. Okay. See, this week the major questions will be on SN1, SN2, and SN-NGP, SNI, and SN-NGP. These are the major questions you will get. Apart of it, now you look at this next reaction, where if you take alcohol, treat that with HX. HX will make it as a protonation. Okay. Where is this coming from? Is this here? If you take an alcohol, try to react that with X minus. And if you're expecting alkyl halide to be prepared, then O minus is coming out. This is impossible reaction. Reason being, this is a weak base and OH minus is a strong base. And you know that weak base can never replace, never be replaced by a strong base. Correct? So I can now not expect that the weak base will go and strong base will come out as leaving group. But the reverse is possible. That is Rx plus OH minus. If it is been treated, I will get ROH plus X minus. So this reaction is feasible. The first reaction is not feasible. But what if I need to produce alkyl halide? In that case, what we can do is that we take this ROH, and instead of reacting that with a salt ion, we react that with an acid, HX. What does HX do? It will first protonate it. It will make this as ROH2 plus. And now X minus will attack on it, making this as Rx plus H2O. Now if you notice, X minus is a stronger base, water is a weaker base. So this time the reaction is feasible because now this is stronger, water is weaker. So you remember the leaving group should always be weaker than the attacking group. Weaker base than the attacking group. Then only the reaction will be favorable. So to make the alkyl halide preparation, we need to first convert them into protonated form. So OH need to be converted into OH2 form so that X minus can attack more easily. So this is what we call it as a protonation. First protonation is done, then X minus will attack. Now, whether this will form carbocation or not, that depends upon the R value. If the R is secondary, tertiary, allyl, benzyl, which will make the carbocation stable, then we'll get R plus and water will come out. And on the R plus, X minus will attack. If the R group is primary or methyl group, then SN2 will happen. Notice this. Rate of reaction is directly proportional to the stability of carbocation. So 3-degree alcohols will make a faster reaction than 2-degree, 1-degree and methanol. And 3-degree allyl will have much faster reaction than only allyl and without allyl, simple secondary. And rate is always proportional to acidic strength. Like if you have HF, HCl, HBr and HI. HI bond breaking is more easily compared to HBr, compared to HCl, compared to HF. Okay. And HF being a weak acid, right? This yield is very, very poor. HCl is used with Lewis acid anhydrous zinc chloride. So if you make this reaction with HCl, that is HCl plus anhydrous zinc chloride, I'm not taking water. Why I'm not taking water? If I take water, have you noticed this reaction? Product is forming water again. Based on Le Chatelain's principle, if the product water concentration increases, reaction might go again in the backward direction. So here reaction would mostly lie in the backward direction if you take aqueous solution. What if I want the reaction to go in the forward direction? Then I need to take anhydrous condition. That's why we take anhydrous zinc chloride and add HCl to it. And this reagent is called as Lucas reagent. HCl plus anhydrous zinc chloride is called Lucas reagent. It will make a reaction called Groove's reaction, where alcohol plus HCl in the presence of anhydrous ZnCl2. If it gives RCl, correct? This R has to be formed only by secondary, tertiary, or benzyl position group, or anything which favors SN1, that is stable carbocation. HBr is quite strong, but we usually use catalytic amount of H2SO4. Okay. HI is strongest acid and does not uh, uh, have any other support. It does not require any other support. Like anhydrous zinc chloride is not required. HBr requires slight a bit of H2SO4, but otherwise HI it requires nothing else. Direct reaction can take place here. Okay. Let us understand what is Lucas test now. Lucas test is mainly used for distinguishing 1-degree, 2-degree, and 3-degree alcohols. We learned what is Lucas reagent already. This is Lucas reagent, HCl in anhydrous zinc chloride. Imagine if at all I have a tertiary alcohol, I use Lucas reagent here. What does Lucas reagent does? First it will protonate here, OH plus, and this OH2 will be left, leaving behind a carbocation. Then Cl minus can attack from the top or from the bottom and prepares a compound here. And this alkyl halide is a white turbidity. It is a white turbidity. This tertiary alkyl halide is a white turbidity. Okay. So you can see as soon as the Lucas reagent is added in the solution of 3-degree alcohol, you will see a white cloudiness will start forming here immediately. If there is an immediate turbidity or white cloudiness, which means it must be 3-degree or very stable carbocation. Second, if you have R and R, this is secondary alcohol. Lucas reagent is added. Usually here also SN1 is favored. A very small amount of SN2 composition is favorable. Here also you will see a white turbid of alkyl halide, but this will take some time, 3 to 5 minutes. Okay, some books give it as 3 to 10 minutes. It's still the same. Okay, 3 to 5 minutes, 3 to 10 minutes. If this range is given, you have to think in terms of secondary alcohols only. So this will give you secondary alcohol here, right? So secondary alcohols will give you turbidity in 3 to 5 minutes. Primary alcohol, if you have primary alcohol, will never go for SN1 mechanism because carbocation is not stable. So it would go for SN2 reaction, but the reaction happens extremely slow. It is so much slow that it might take 30 minutes or it might require heating for a reaction to complete. Okay. So remember, rate of SN1 is very high compared to that of SN2. So rate of reaction, tertiary is more greater than secondary, than primary and methanol. Here SN1 is favorable, here SN2 is favorable. Just by checking out the molecule of alcohol, we should be able to comment that whether it will take less time or more time. Got it? That is, for example, if you take alcohol here, this is 2-degree alcohol. 2-degree alcohol will take 3 to 5 minutes. Here you can see second case. This is 3-degree alcohol. So immediately turbid will be immediate. 2-degree, 3 to 5 minutes. Here there is an allylic position. Remember, allylic carbocation, benzylic carbocation, these are very stable ones. They'll give immediately. So don't just look at 2-degree. It is actually 2-degree allyl. Here also it is 2-degree, but it is benzyl, 2-degree benzyl. So immediately you will get. Phenols will never give turbidity. One side there is phenol, but the other side there is benzyl. So immediately you will get. There is chloride here. You can remove chlorine first, bring OH here, correct? And that will also give you immediate turbidity. So whether it is OH group or whether it is chloride group, both will give turbidity immediately. Okay. Next, 1-degree, 30 minutes and above. 3-degree immediately. 3-degree allyl immediately. Right. Now this is, if you notice, this is 1-degree. Don't think like, sir, I can make stable carbocation. Right. It is the first carbocation which is important for us. Here the first carbocation is 1-degree. So this will take longer time. Here it is benzyl position immediately. Here it is OH group directly connected on benzene. So phenolic group, no. Here it is primary, so 30 degrees. Here it is secondary to 16 degrees. I mean, 3 to 5 minutes. Okay. Clear, everybody? So this is what is the question that will be asked to you based on Lucas reagent, which will happen immediately, immediate turbidity, or which will take some time, which turbidity will take some time. Okay. Clear, everyone? Right. Next. If it is with HI or HBr, if it is with HI or HBr, with HI, if this is at secondary position, immediately carbocation will form. I minus will attack from both the ends. So you will get racemic mixture. If it is HBr, positive charge will form. Again, Br can attack from both the sides. Racemic mixture will happen. If it is with HCl, carbocation will form because it is at second tertiary position. Cl can attack on both the ends. You will get racemic mixture. Okay. So these are the stereochemical reactions which you will notice, which are happening via Lucas reagent. Everybody clear on that? I hope all of you understood that. What exactly is going on here? You know, how the reaction is taking place. Okay. Now, let me summarize everything in terms of how the reactions are taking place, whether it is SN1, SN2, in what case SN1, SN2 is happening, correct? This is something which we know to which we need to know how exactly the reactions are taking place. After that, we will discuss the next concept, which is about Grignard's reagent. Clear? I hope all of you got an idea about what to think in terms of substitution, in terms of elimination. So our next concept is about understanding substitution versus elimination. How exactly substitution versus elimination will take place, and so on. Just check it out. This I want you to write down simultaneously. Substitution versus elimination. Substitution versus elimination. Okay. See, if we are sure that we have a good nucleophile and it is not acting like a base, right? If it is not acting like a base, so only nucleophile. So we will say this as first case, nucleophile character only, nucleophile only. Especially cases like I minus, ACO minus, N3 minus, Br minus, HS minus, right? These water, they will only act like nucleophile. Okay. So if they're acting only as nucleophile, guys, then what are the expected ones here? Suppose if the substrate here is, if the substrate here is 1 degree, okay, substrate, substrate is 1 degree, 1 degree alkyl halide, then the mechanism will definitely go through SN2. Okay. Next, next. If the substrate is 2 degree, then the mechanism will happen SN1 also, SN2 also. Both will happen. Okay. If it is 3 degree alkyl halide, then the mechanism will only happen via SN1. I hope all of you clear with that, right? This is something which you need to understand. In what case, what would happen? Clear? Right. Second case. Second case, if you notice, this time base only. This is not acting like a nucleophile. Base only. So that means these reagents will only act like base. They are not very good nucleophiles at all. For example, R minus, H minus, NH2 minus, NH2 minus, okay, uh, RC, CH double bond C minus, like this, okay, or tert butoxide, LDA, okay, tertiary amines. These are generally going to act like bases only. They will hardly act like nucleophiles. Okay. In such case, whether it is 1 degree, 2 degree, or 3 degree, you will only notice A2 reactions. These are all going to be E2 reactions only. Clear, everybody? So if you have only base, it could be always going to be E2 kind of mechanism. Okay, make a note of it, everyone. Next, third case. If you have both nucleophilic as well as basic nature, nucleophilic nature also and basic nature also, and both. These reagents are those which are typically like OH minus, RO minus, ammonia, right? Cyanide. We have, what else we have? PHO minus, acetate, acetylene, sorry, acetylene case. These are, which can act like both nucleophile also and base also based on the situation. Okay. So now, if it is 1 degree substrate, then E2 will be minor E2 will be minor, and SN2 will be major in this case. SN2 will be major. Okay. And if it is second degree, then E2 will be major and SN2 will be minor in this case. Got it? And if it is 3 degree, there is no SN2, it will always going to be E2 mechanism only. Got it? It is always going to be E2 mechanism only. Clear? Now, all of these are supposed to be strong nucleophiles. So keep a note of that. So these are all strong nucleophiles and strong bases. So their nucleophilic strength is also strong, basic strength is also strong. Accordingly, you have to behave. Okay. Fourth one. Fourth one. If you have again based on both nucleophile as well as base, nucleophilic as well as basic, both, but this time these are all weak ones. Whatever we are talking is all weak ones. That is, I have H2O, weak, alcohol, or COOH, like this. Okay. Uh, that's it. These are the ones which I've been using. Okay. Very weak ones. Phenol, for example, I can take phenol also, like this. If you take weak bases, weak bases or weak nucleophiles, correct? In that case, first case, if it is substrate, correct? You have to have two cases here. Substrate, within the substrate, are we using heat or not? Okay. So if you are going to this substrate, one is with heat and one is without heat. Okay. So if you are using heat here, 1 degree with and without heat. If it is without heat, it is definitely going to be SN2 as major. And if it is with heat, then it is E1 as major. E1 as major. Clear? Similarly, same logic here also. Suppose if at all I'm going for this case with heat and without heat. With heat, without heat on secondary case, it will be usually SN1 major. And with heat, it is E1 major. And tertiary also the same logic. If it is with or without heat. If it is with heat, uh, SN1 as major. I mean, without heat, this is major. And here, E1 as major. E1 as major, right? So these are the cases. Okay, clear? Everybody, write this down properly. Keep it in front of your desk always. Okay. Whenever you're studying, whenever you're solving questions, this will be very useful. You can directly check out which case you should go for and accordingly you can solve it. Clear? I hope this part is clear, everyone. Yeah. Done? Right. Now, before going into next topic, which is about what is the question? Sir, once show first one. Okay. Check out. Right. We're actually going to start the alkyl halides now because this is all the background we require. Okay. Although now it becomes more easy without mechanisms. Now this is all without mechanisms. Sure, Pranati, I'll send it. Okay. Right. Notice this. So first, starting with the synthesis of alkyl halides, preparation. Preparation of alkyl halides. Okay. First, this is from alkanes. From alkanes. We have already learned this in hydrocarbons. So now we don't have to do mechanisms. We can directly go ahead and understand what might be happening. If you have RH, if you treat this with Cl2 and H nu, I will get this as RCl plus HCl via free radical mechanism. Free radical mechanism. Okay. And this free radical mechanism is more preferable for chlorine and bromine only. Okay. Next, RH can also be treated with SO2Cl2 in the presence of H nu. This is also a free radical mechanism plus HCl plus SO2, right? This is more selective mechanism. More selective mechanism. Okay. What does that mean? Suppose if you have a compound like this and you are treating that with Cl2, H nu, correct? So then I might get this also product, right? I might get this product also, and I might get this product also in sizable amount, and this product also in sizable amount. But if you use SO2Cl2 in the presence of H nu, while in all of these cases, this is major here, in all of these cases, this is major. While SO2Cl2, if you notice that, right, then this will be 99.9%. So now you can imagine, just like bromination is highly selective. If you want chlorine to be highly selective, then you use SO2Cl. I hope the detail is clear, everybody. This is first from alkanes. Okay, clear. Second from alkenes. From alkenes, how do we prepare it? Suppose if you have an alkene like this, and I want to prepare alkyl halide, then we do HX reaction. In HX reaction, we will get this as X. The reaction's name is hydrohalogenation. Hydrohalogenation reaction. Clear? It follows Markovnikov's rule. Markovnikov's rule, and it happens via carbocation. The addition reactions before in the alkenes when we learned. So again, I don't have to go through the mechanism. So I'm hoping that this point should be recalled by you. Okay. Clear, everybody? This is about how the reactions work here. Here. Next, in case if you have HX, that is only HBr in the presence of peroxide, if it is being used in the presence of peroxide, then Br will come here. Here. Now, if you notice the points in this case, here it is hydrohalogenation, but this time it is anti-Markovnikov's addition. Anti-Markovnikov's addition. This is via free radical. Free radical mechanism. Clear, everybody? These are all synopsis, everyone. We don't have to again do all the mechanisms. I hope you should be able to recall that. Okay. Next reaction is when you have Br2 in CCl4. Br2 in CCl4. If you have Br2 in CCl4, will get Br here and Br here. Correct? So this is an halogenation reaction. This is called halogenation reaction. Okay. It will happen via, you know, halonium bridge. Halonium bridge formation. Because first bromine bridge is formed, then it will go for an anti-addition. Anti-addition. Okay. It will go for an anti-addition. No carbocation is formed. No carbocation or rearrangement. No carbocation and rearrangement observed in this. Correct? So this is about getting bromine added. Okay. Next, if you have this reactant treated with NBS, N-bromosuccinamide. Okay. NBS, or you can write it as Br2 in the presence of Br2 at 600 degrees centigrade, high temperature. Either NBS or Br2 at 600 degrees centigrade. This will always give you a radical mechanism which will be allyl substitution. So Br will be substituted here. So this is allylic substitution. Allylic substitution. Clear. And via radical mechanism. All right. I hope all of you are able to recall this. This is what we have done it earlier. Correct. Allylic substitution, and this is the product you will get. Right. This is all we have learned in alkenes. Okay. These are all a part of alkene reactions. Next, third one is from alkynes. From alkynes. From alkynes, we have RC triple bond CH. If you add HX, sufficient amount of HX, so uh, first addition will be Markovnikov like this. This is like a Markovnikov addition. Again, second addition, when you do, the halogens will always come on the same location. There is no hydrogen here. So halogens will come on the same location here. So we'll make this as CH3. So these are called geminal dihalides. Geminal dihalides. These are geminal dihalides. Okay. Similarly, if you have RC triple bond CH in the presence of Br2 CCl4, all the bromine will get added on both the carbons here, like this CH, Br and Br. So both sides bromine will get added. Okay. Then from alkyl halides. Alkyl halides to alkyl halides. I mean, we are making alkyl halides to again make alkyl halides. This can be done via first Finkenstein reaction. Finkenstein reaction where we take Rx, this X could be chlorine or bromine, and we treat this with NaI in the presence of acetone. We will get this as Ri plus NaX getting precipitated. This is Finkenstein's reaction. Then we learn Schwarz reaction, which is Rx plus, so yeah, Rx plus Ag, AgF or SbF3 or COF3 or HgF2, any of this, if you treat it in the presence of ether, so we will get this as Rf plus AgX getting precipitated or others getting precipitated. This is Schwarz reaction. So I hope this point is clear, right? What is Schwarz reaction? How it is been done. Next, fifth one from alcohols. Just now we have learned Lucas reagent. That is the same thing. If you take ROH plus HX with some heat is essential to make the reaction more drive in the forward direction. So we will get this as RH plus H2O. Okay, and heat is also essential to remove away the product here. Okay, this is first one. Second, ROH plus HCl in the presence of zinc chloride anhydrous. Then we'll get this as RCl plus H2O plus Zn, right? So we will get this as, sorry, this H2O will be part of Zn. So we'll get this as H2O with Zn Cl2, correct, with minus. This kind of complex will be formed here, right? So here, this is Lucas using Lucas reagent, using Lucas reagent. Just now we have seen it. How do we get this Lucas reagent to be done here? Okay. As an example, if at all I have to give you an example here, let me take one example. If you have, we have done these examples already, lot of them. So if you have OH here and you are treating that with HCl, it's not Lucas reagent. I gave only HCl here. So in that case, first OH2 will be formed. Carbocation is formed here. Carbocation will undergo rearrangement here. Positive charge will come here. Then Cl minus will attack on it, by which you will get fluorine coming here. So this is the major product which you will get. Done, everybody? Correct. Now, in case of primary positions, if you have, right, in that case, we need to add little more boiling form of, solution. That is, suppose if you have neo type of a group here, okay, or let's say H here, methyl here, correct, and then we have OH here. So if I want to react it via carbocation, that means I have to take HBr in a boiling condition. Okay. Then only first carbocation will be formed here. We have methyl and hydrogen. Then the rearrangement will take place. So rearrangement will make methyl here with carbocation. And that's when Br minus will attack. And finally, we will get the product as Br here, methyl here, methyl here, and methyl here. This is what you will get. But the condition has to be boiling. Okay. Same is the case with HI. HI in a boiling condition also will give you the carbocation formation. Clear? So always remember, if it is primary, secondary position, boiling condition is essential. If it is second, tertiary condition, no boiling condition is essential. Got it? I hope this part is understood, everybody. Okay. Right. Next, action of PCl3, PCl5, and SOCl2. We learned this exclusively, how the reactions happen. So 3 moles of ROH plus PCl3. This was the first, this was the last reaction we learned actually. So we got this as 3 moles of RCl plus H3PO3. This was reaction 1. And it is happening via SN2 in ether. Next, we had 1 mole of ROH treated with PCl5. This also went via SN2 mechanism in the presence of ether to get 1 mole of RCl plus POCl3 plus HCl. Third reaction, we had 1 mole of ROH treated with SOCl2. This went via SNI mechanism in ether to get this as RCl plus SO2 plus HCl. Okay. This is the best reaction for better yield because SO2 and HCl, both of them are going as gas. But if I want some kind of an inversion within the molecule, then I have to take SOCl2. This time it will happen via SN2, but this has to be in the presence of pyridine. Then I will get this as RCl plus SO2 plus pyridinium chloride. Okay. This is called Darzens reaction. Darzens reaction. Okay. So this is a complete synopsis of these reactions which we learned, everybody. Check out properly. This you need to practice a lot of times because this is the area which is touched many times in the exam. Okay. How these reactions work. We have learned the thorough mechanism also on this. So I don't think you should have any issue with this. Done? Everybody? Chalo, sixth one. Sixth is from carboxylic acids. From carboxylic acids. How do we get alkyl halides? Okay. First, RCOOH has to be treated with moist Ag2O. This will make an acid-base reaction to make this as RCOAG plus H2O. This is a silver salt of carboxylic acid. This is a silver salt. Okay. This reaction from carboxylic acid, the reaction's name is Hunts-Decker reaction. First, we need to get silver salt. Then we need to add this silver salt with Br2. On treating with this, we will get AgBr as a precipitate. Plus, we will get this as RC double bond O OBr as an intermediate. This is the intermediate which you will get here. Now, this intermediate will undergo radical mechanism with OBr here. So, this would undergo radical formation to get this as RC double bond O, RC double bond O dot plus Br dot here. And you know that this RC double bond O dot is unstable form. It will become R dot plus CO2. And this R dot plus Br dot will eventually become RBr. Okay. So if I put it as an overall reaction here, overall reaction is this RCOAG plus Br2 is becoming RBr plus CO2 plus AgBr. So this is the overall reaction. Even if you don't know the mechanism, that is fine. You just need to know what are the products coming. That's all. Okay. Here, just like how we had silver salt, we can have mercury also. So we can react in a similar way. RCOOH plus HGO, right? Just like moist Ag2O, here we need to have HGO plus Br2. So that will make again RBr plus HgBr2 as the precipitate plus CO2 and H2O. These are the products you will get. Alkyl halide products you will get. Okay. So I think this part is clear, everyone. Yeah. Right. The yield of the reaction, if you notice, yield of the above reactions, both, okay, will be better if it is 1 degree, 2 degree, and 3 degree. So don't think like it should be 3 degree because you need to make sure that the carbon dioxide is leaving. Carbon dioxide will leave more easily when it is at 1 degree position. Yeah. So the reaction would be this way. Okay. Now, suppose uh, instead of Br2, if at all I use I2, okay, if I2 is used, If I2 is used, then what will happen to the reaction? So imagine like this, I have R C double bond O OAG. This is the silver salt of acid that when you treat with iodine AI2 here, right? So first we will get this as AgI. Okay? First we will get this as AgI, clear? And because 2 moles of this silver will form AgI here, and this 2 moles of will form ester here. So now we will get this as R here plus CO2. Okay. So here you will not get alkyl halide. Here you will get more of ester. This is a major product here. This is a major product. This is the importance when you have it with what do you say, I2. Here, I hope all of you understood this point. Okay. But this is only when this is excess. So this is in excess. So if it is in excess. Now suppose if I2 is in excess, then we can expect alkyl halide to form. That is, if you have R, C double bond O, OAG is present, plus I2 is been given, and this is given excess. In that case, nothing will happen but AgI plus Ri plus CO2 will form. For it. So you got to be clear in which case what would happen. Then everybody. So these are all the preparation reactions, guys. Okay, as per NCRT also, these are the points which we need to know from preparation point of view. Okay. Now let's see what are the physical characteristics. Physical characteristics or physical properties. Right. Firstly, an alkyl halide will have C and X bond like this, which means this will have delta positive, this will have delta negative. So there is a dipole moment always there. Okay. So because of this dipole moment, there is always a partial charge present on it. Okay. There is always a partial charge present on it. So dipole moment is always greater than zero in alkyl halides. Clear? So there is always some amount of partial charge present on it. And you can notice that this is an sp3 carbon. So accordingly, you will have some amount of polarization. So polarized, polarized with some dipole moment, with some dipole moment. Okay. Now the dipole moment depends upon how much is the electronegativity. Higher the electronegativity, more is the polarization. So more is the dipole moment, which you will notice. Clear? Now, what all things we should learn first is first bond length, how the bond length is catalyzed. If you notice CF and CCl and CBr and CI. So obviously CI is much higher in bond length. And if you compare exactly the values, 1.38 here, 1.78 Armstrongs here, 1.94 Armstrongs here, okay, and 2.14 Armstrongs here. So this is the bond length. Okay. Now see the critical thing here. You know the bond length, we know the electronegativity. Electronegativity, fluorine is greater than that of chlorine, bromine, and iodine. Now, if you measure the dipole moment, because dipole moment mu depends upon charge also. It will depend upon the distance also. Q into D, isn't it? It will depend on charge also and distance also. In that case, what has been noticed? If you compare CI, CBr, and CF and CCl, if you compare this, this is coming out to be 1.29 dB units. This is 1.48 dB units. This is 1.51 dB units. And CCl will be 1.56 dB units. So you can see the product is dominant for carbon-chlorine bond. So dipole moment of carbon-chlorine bond will be greater than that of dipole moment of carbon and fluorine. Okay. So this is the first characteristic which is about dipole moment you should learn. Everybody clear on that? How the dipole moment is changing. Okay. Now, this alkyl halides could be primary kind also. They could be 2 degree, I mean, two alkyl halides also, three alkyl halides also. So, first, let us list out dipole moment for CH3X type. CH3X type. CH3X types, if you notice, fluorine, bromine, chlorine, and iodine. If this is the case, the value was found to be 1.82 dB units. Okay. This is 1.94. Sorry, chlorine here. Chlorine, bromine, and iodine. Okay. 1.94, 1.79 D, and 1.64 D. This is for complete molecule here. And if it is for mu being CH2X2, CH2X2 here, then it is 1.97, 1.60, 1.45, and 1.1 dB units. Okay. Next, if it is about mu being CH2, sorry, CHX3, CHX3. If it is for fluorine, it is 1.65 dB units, 1.03 dB units, 1.02 dB units, and 1 dB unit. And if it is CX4, it is 0, no dipole. Huh? So I hope you got an idea about how the dipole moment varies. Okay, next. If you notice second issue, which is about boiling point. Boiling point, generally, if you have alkyl, suppose if you have CH3 compared to that of CH3, CH2Cl, same number of carbons, definitely alkyl halide will have more because it has more more molar mass, and a small amount of dipole moment is also helping. Second, if you have CH3F, CH3F, CH3Cl, CH3Br, and CH3I. Always remember the molar mass of the iodine is very dominant. Okay? Molar mass is dominant factor. Dominant factor. So that's why halides will always have more boiling point compared to that of bromines, chlorines, and iodides. Okay, right. Obviously, if there is a branching, definitely we will have less amount of boiling point. So if you have 1, 2, 3, 4, 1, 2, 3, 4, 5, then we have X here, 1, 2, 3, 4, 5. Okay. And then we have 1, 2, 3, 4 with 1, 2, 3, 4, 5 X here. And then we have 1, 2, 3, 4 and 1, 2, 3, 4, 5 and X here. Okay. So if we compare this, more the branching will have, less will be the boiling. This is how the boiling point will vary. Okay. Got it. Next, if you notice densities, okay. This just we need to remember it as a point. We don't need to analyze anything here. So generally all alkyl fluorides and chlorides, alkyl fluorides and chlorides are less denser than water, while bromides, and iodides are more denser than water, H2. Okay. So this is one part which you need to know here, which one is being more or less. Okay. Clear. But if you have two chlorides here, alkyl halide, halides with more than two chlorides, two chlorides are denser than water, are denser than water. Done. So these are the 2 points which we need to know. Uh, most of the alkyl halides are soluble in benzene, ether, and chloroform. Okay, they are very sparingly soluble in water. Okay, or I could say almost insoluble in water, but they are sufficiently soluble in benzene, ether, or chloroform. Okay? So if you see the solubility part, solubility, let's say they are insoluble, insoluble in H2O, but soluble in benzene, CCl4, CS2, and chloroform, CHCl3. Right? Ethers also, sorry, ethers. In this case, they are soluble. Done. So when it comes to physical properties, these are the four properties, main properties which you need to learn. How the density, solubility, boiling point, as well as dipole moment characteristics are changing. I hope all of you understood this point. So what to do? Now, chemical reactions, if you notice, chemical reactions of alkyl halides. First reaction, being, okay, uh, nucleophilic substitution. These are all the things which we learned as SN1, SN2, correct? SNNGP, all of those cases. Examples, if you take RX added with H2O, right? So we will get this as ROH2. This is solvolysis reaction. And then H minus will be removed. So we'll get this as alcohol plus HX minus X here. Okay. This is the product we will get. Clear? So wherever we see aqueous, okay, aqueous NaOH, aqueous KOH, moist Ag2O, and H2O, they all will undergo SN1 or SN2 depending upon the alkyl halide, whether it is 1 degree, 2 degree, 3 degree, depending upon that, accordingly we'll get the reactions. Okay. B is Williamson synthesis. Williamson's synthesis. I'm not going into the details of it. We have learned it already. So we learned that Rx plus alkoxide, RO minus, when you have, you will get this as ROR plus X minus. This has to happen via SN2 mechanism. Then it is called as Williamson synthesis. We have learned the feasibility, in which case it will happen or which case it will not happen. Correct? Next. Within the Williamson synthesis, other methods to prepare, other methods for ethers, ether synthesis, ether synthesis. Okay. What are the other methods? See, other methods are this. If you take 2 moles of alkyl halide and treat that with Ag2O dry, not moist, dry. If it is dry, then I'll get this as ROR plus 2 moles of AgX. If it is wet or if it is moist, I'll get the same thing as alcohols. That's the only difference. Okay. This is one method. The other method is you take an alkyl halide, RX, you take an alkyl halide and treat that with ETOH or something like that. That is alcohol. When you treat it with alcohol, then we can get this as ROET plus HX, like this. Again, the mechanism is something which you need to understand, in which case it will happen or not. Correct? Next, if you have internal reaction also, internal reaction as in, if you have C here like this, we have OH here and Cl here this way. And then You are treating this in OH minus. So what does OH minus do? OH minus will extract this H plus, and that O minus will attack here so that it can remove that O minus can attack here so that it can remove that chlorine. So what we will get is a cyclic ether like this. So we will get this as a cyclic ether. Got it? I hope this point is clear. Okay. Another reaction which you can notice is this one, where we have OH here, Br here, and if you treat that with Et3N, this is the base. This base will extract proton. So we will get a 5-membered ring like this with Br minus coming out. Right? That is also a cyclic ether. So cyclic ether can be made this. Got it? Next, C reaction is about alkylation. Okay, alkylation on carboxylic groups. Carboxylic groups. Okay, that is if you have something as R dash CO minus Na plus, right? That I have to react with Rx. Again, this will usually prefer SN2, but again SN1 can also be favorable depending upon the uh, position of this Rx. If it is 1 degree, definitely it will favor SN2. If it is 2 degree, or if it is if it is 3 degree, definitely it will favor SN1, right? So here I can say SN2 1 degree, SN2 if it is 1 degree or 2 degree, Rx if it is 3 degree, benzyl, we might get this as RCOR dash via SN1 type of mechanism. This is alkylation which we are doing. Clear? I hope this part is clear, everyone. Okay. Next, D is about uh, preparing peroxides. How do we prepare peroxides? So that is preparing peroxides. Preparing peroxides. Now you notice this, we have Rx plus ROO minus, right? RO minus. Okay. Sorry, HO minus. So I'm making peroxide. So that HO minus will attack. That will make this as ROOH plus X minus. So this is the peroxide group which you will get. Okay. Or if you have 2 moles of Rx and I treat that with Na2O2. So on both sides we'll get R. So this is the product you will get 2 moles of NaX. So this is how you'll get a peroxy group forming. I hope this part is clear, everybody. Okay. Next, if you have any sulfur nucleophiles, how do we respond to that? Okay. Sulfur nucleophiles. Sulfur-based nucleophiles. How do we respond to those questions? Okay, check. Suppose if you have any Rx, treating that with H2S, treated that with H2S, then we can get first as RSH2 plus, just like how water getting added, removing this X minus, and then H plus can be removed. I'll get this as RSH. Exactly how the water behaves, the same thing here. Okay. And same way, if you have, let's say, suppose if you have like this, and we have bromine here, clear? And if you have SH minus been taken, just like OH minus, this will also behave in a same way. So we can have this as SH, we can have this as SH via SN1 mechanism, plus we can have this double bond formation here, which is major product via E2 mechanism, because HS minus is also a strong base, sufficiently strong base. So we can expect this to go via E2 mechanism as well. Clear? Next, if you have RS minus, so that is just like Williamson synthesis. If you have RS minus, we will get this as RSR. So these are called thioethers. These are thioethers. Same reactions repeated. Again, you can see the same type of reactions. Similarly, Rx, if you treat that with S2 minus, just like peroxy groups, we'll get this as thioperoxy groups. Here, this is thioperoxide. Here. So this is disulfide, disulfide alkanes, sorry, disulfide ethers. Got it? Right. The same logic can be applied even if you have SCN minus. If you have SCN minus, it will become RSCN plus X minus. The attack is from the sulfur end. Got it? This is all about sulfur compounds. Nitrogen based compounds. Okay. Nitrogen nucleophiles. If you notice how the nitrogen nucleophiles behave. Okay. First is alkylation. Alkylation, which you also known as ammonolysis. Ammonolysis, because if at all we are adding ammonia to this, what would be the reaction? So if I have explained you already, if this is excess, alkyl halide is excess and ammonia is in less quantity, okay, the reaction will keep on going till it becomes tertiary ammonium salt, X minus. This is major. This is major product. Suppose if you have Rx plus we have excess amount of ammonia here. Ammonia is excess here. In that case, 1 degree will be excess here, R NH2. So this will be major in this case. Got it? So it all depends upon which one do you want to make it as a excess or not. If you notice some example, internally also there is an attack that could happen. So we have 1, 2, 3, 4. Suppose I have NH2 here and I have Cl here. Okay. So internally, we will notice no, as such reagent is required. But if you take it as a base here, so lone pair will definitely attack on this position, remove out chlorine. So that makes it a 5-membered ring like this, NH. So this is the product you will get. Okay. Clear, everyone? Right. Next, azides. Okay. Azides are formed here. Azides are N3 minus groups. N3 minus. These are azides. So if you take any alkyl halide, treat that with N3 minus, you will notice that it will form RN3. So this is the azide form. Okay. Structurally, azides look like this: N double bond N double bond N. Right. This is plus minus and minus. This is the azide form. Okay. N3 minus. Correct. These are the nucleophiles which you will notice. Okay. If you have a carbon nucleophile, lastly, carbon nucleophile. See, carbon as a nucleophile will act very rare, right? This one is E, oh, sorry, E, F, G. Carbon as a nucleophile is very rare unless it is a triple bond. Double bonds and single bonds, they will only act like bases. So plus R dash X. So in that case, I can say this as this will become RC triple bond C R dash. This is the reaction we can expect. Okay. How to behave with ambient nucleophiles, KCN, AGCN, KNO2, AgNO2, that I discussed already. What would happen in case of, AgNO2 or KNO2 and so on. Okay. Just to be reminding about that. So check out. In case if you have ambidentate nucleophiles, ambidentate nucleophiles. Okay. Specifically when you have NO2 and AgNO2. So if it is Rx and this is 1 degree and 2 degree, if it is 1 degree and 2 degree, and I'm treating that with KNO2, at KNO2, then this will go for SN2 type of mechanism. and you'll get this as RNO2 plus RONO2, RONO. And major product is this one, RNO2. Clear? If it is 1 degree and 2 degree. Understood? Uh, if you notice why it is major, like if you take KNO2, why it is to be major here? Here, NO2 here is coming as this way, K plus and O minus N double bond O, correct? N double bond O here. So it is the attack of O minus which is observed, correct? Right. Sorry, here I've written major to be this one, major here. Okay. So O minus is going to attack on R. So that's why this will come out as major. This will come out as minor. Here. So this is how it will attack. Now, if you have 1 degree, that is alkyl halide is there here. So Rx is there, and this is 3 degree here. And I took this as KNO2. Well, this will go via SN1 reaction now. This would happen to go via SN1 reaction. In that case, you will notice that RNO2, RNO2 this one, this time will be major, and RONO will be minor. Similarly, let me take out the same reaction here, just that I need to change for AgNO2. In case if it is about AgNO2, AgNO2 structure will be like this. AgNO2. Because it is covalently bonded. It is covalently bonded here. Okay. So this time, this will be major. Nitro will be major. And this will be minor. Major and this will be minor. And second case, the other way around. This will be minor. And this will be major in this case. So how they are opposite in SN1 and SN2, just that is something which you need to know. Clear, everybody? I hope this part is done. Lastly, reduction reactions. This is all nucleophile, which is first case. Second is reduction reactions. If you notice reduction reactions first, if you take Rx and it is 1 degree or 2 degree, if you treat this with lithium aluminum hydride, you will get this as RH. Lithium aluminum hydride, you will get this as RX. And if it is 3 degree, then you treat this with lithium aluminum hydride. You will get alkene. Alkenes via E2 mechanism. This is about lithium aluminum hydride. Okay. If you have RX with 1 degree and 2 degree, sorry, only 1 degree, only with 1 degree. If it is NaBH4, no reaction will take place. If it is with 2 degree and 3 degree, with NaBH4, then it will give alkanes. That is RH. This is with NaBH4. Okay. Next, exclusively, if you have 3 degree alkyl halide, only 3 degree alkyl halide, right? Then, if you treat that with Bu3SNH or you use pH thrice SNH, tin hydride, that will give you alkyl halide. So, alkanes. So, specifically, this is used for the purpose of 3 degree only. Correct? Next, activated metals like RX, if you have 1 degree and 2 degree, and you take zinc in dilute HCl, These are activated metals. They'll always give you alkanes. Okay. Zinc and HCl is an activated metal. Okay. Or, any kind of metal uh, in case of HCl, or you can take in case of NaOH also, dilute NaOH. In both the cases, you will get alkanes. Correct. Next, if you have Rx and you treat that with Grignard's reagent, sorry, magnesium. I think this we can discuss it in Grignard's reagent only. We will not discuss that here. Yeah, and if you treat that with sodium metal, right, and I take 2 moles of it in the presence of ether, then you know that this will become R and R, which we call it as Wood's reaction. This is Wood's reaction. So these are all the recap of what we learned. If you take Rx in the presence of zinc only and heat it, right, then we will get this as R and R plus ZnX2. This is called Frankland's reaction. Frankland's reaction. And lastly, Korehouse synthesis, if you recall, we will get this as Rx plus R2CuLi. This is R dash. So then I'll get 2 moles of R dash and R plus Cux plus Lix. So this is Korehouse synthesis. Korehouse synthesis. Okay. So these are all the things which you need to know. Last thing is metals Rx. If you have 1 degree and 2 degree in the presence of H2 and nickel, or H2 or ranonickel. Any of these will get this as alkanes. Right? Again, you'll get alkanes. So these are all the reduction reactions, guys. Just a recap of what we learned from alkenes. These are all we learned as a preparation of alkenes. If you go to the notes of alkenes, you will find all of these reactions again as a preparation of alkenes. Got it? We already learned about elimination. So you just have to recap the elimination reactions, whatever we have learned. That's it. So this is how much you have it, from alkyl halides. One part of alkyl halide, which is about Grignard's reagent only, exclusively about Grignard's reagent. That is something which we'll learn it tomorrow. Got it? So I hope you guys got an idea or the